the stream's going.
Yes, yes. The notifications are popping up that you're now streaming. So.
Right.
So where is this picture from?
That's the bottom of the driveway where I'm living right now.
Oh. Okay. Nice.
Yeah, it's a pretty lovely spot.
So you have fireweed there.
We call them lupins, but they might be the same. I don't think they are the same, but they look similar.
Yeah, no, they're not the same, but yes.
End of the road. Yeah, sorry, you got my my reference, the metaphor of the picture.
Well, it looks like the middle of the road.
Well, the road continues on.
Yes, indeed. Exactly.
But the driveway is also the end of the road in a certain sense. So when you're heading home. Okay, I think we'll gently get started. So welcome back, everyone, for the last lecture of this course. So I think my plan is to finish the calculation we were in the middle of last lecture, then take a brief pause to mention a couple of administrative things, and then continue talking about the structure of the local limit of the minimum spanning tree on a complete graph. So feel free to ask questions as usual. So where were we? We were looking at, so this object M, which is the component of the minimum spanning forest on the PWIT. So the wired minimum spanning forest of the Poisson weighted infinite tree containing the root. Okay, and so we derive the identity that the total weight, the expected total weight of the edges of this tree, which contain the root. So those are these Poisson weights. And this was the integral from 0 to infinity lambda 1 minus theta lambda squared. D lambda. Okay, and remember, so this theta lambda so this is the survival probability for a Poisson lambda bien-aimé tree. So this satisfied the identity e to the minus 1 minus theta equals e to the minus lambda theta, and that's just derived by doing the one-step calculation, saying the probability that this bien-aimé Poisson tree is finite, you can write as a sum over k, the probability that the root has k children, times, and then if it has k children, then for the tree to be finite, all of those children have to have finite subtrees, so you get this same probability to the power k. Okay, and then, so if you remember, this is 1 minus theta lambda, and use the definition of the Poisson distribution, then you derive this identity. Okay, so using this, we're going to prove that this expected total weight incident to the root in M was 2 zeta 3. So now that boils down to showing that if we integrate lambda 1 minus theta lambda squared d lambda, that we get 2 zeta 3. So let's prove that. So this is quite a pleasant calculation. It's a couple of, it's a little bit surprising. I mean, this is a relatively concrete formula, right? Here we have, this is the sum of 1 over k cubed for k at least 1, right? Whereas this theta was defined via this implicit identity, so it's maybe a little bit surprising that we can get something so clean out, but with a couple of integration by parts and a change of variables, the calculation doesn't end up being too bad. So first, if you do integration by parts here, so you integrate up the lambda, you'll get lambda squared on 2, and here you'll get it like 2 theta prime. That's the first integration by parts. And that gives you, so that this is the same as integral 0 to infinity lambda squared on 2, so minus 2 theta lambda minus theta prime lambda d lambda, which if we just cancel out the minuses and the factor 2's, gives us, so the integral lambda squared theta lambda theta prime lambda. Okay, and now, so because theta is the Poisson survival probability, we know that it's 0 for lambda between 0 and 1. So we only have to do this integral from 1 to infinity. The integrand is 0 from 0 to 1. Okay, and now I'd like to use the defining identity to rewrite lambda here. So if we use, so 1 minus theta lambda is e to the minus lambda theta lambda. Let's take logs. So that tells us log 1 minus theta is minus lambda theta, right? So in other words, lambda is minus log 1 minus theta over theta. Okay, so let's plug that in here. That tells us that this integral is the same as the integral of log squared 1 minus theta. And now the theta squared on the bottom cancels once with the theta on the top. We get over theta lambda, and then we still have theta prime lambda d lambda. Okay, and now there's a natural change of variables just given by noting we have theta prime lambda d lambda here. So let's view theta as the variable of integration rather than lambda as the variable of integration, and that will get rid of the implicit function for us, right? So as lambda goes from 1 to infinity, theta goes from 0 to 1, right? So I'm setting t to be theta lambda here, and then this integral becomes the integral from 0 to 1 of log square. This is just the dt now. So we get log squared 1 minus t over t dt. Okay, and so now we're almost done. Now we'll just take, so the right thing to do turns out to be to take, so u to be minus log 1 minus t. Okay, or equivalently, t is 1 minus e to the minus u, so that we get dt is e to the minus u du. Okay, and what are the terms in this in the integral here? So log squared 1 minus t is u squared, and 1 over t is 1 on 1 minus e to the minus u, right? And so then the whole integral becomes an integral now from, so as t goes from 0 to 1, this minus log 1 minus t goes from 0 to infinity. So we get integral from 0 to infinity u squared e to the minus u du on 1 minus e to the minus u, right? But now let's just note, e to the minus u on 1 minus e to the minus u. That's the sum from 1 to infinity of e to the minus ku, right? That's just a geometric sum started at 1. Okay, and so this whole integral is the same as, so the sum for k from 1 to infinity of integral of u squared e to the minus ku du, right? And that's just like a gamma integral. That's, 2 integration by parts tells you that this is 1 over k cubed. So we get, 2 over k cubed. So we get sum from k from 1 to infinity, 2 over k cubed, which is 2 zeta 3. Okay, so the sort of, I don't know, the first time I, saw this calculation, it felt a little bit magical. And then after working through it a few times, it starts to feel less magical. I mean, the heart of the calculation is getting rid of the dependence on this implicit function. So doing a change of variables to get away from theta. And so making a theta prime appear so that you can do that is kind of the key at the start. And so so that sort of, if you have the idea that you want to get rid of the implicit function, and then have the idea of doing an integration by parts to do that, once you get down to this integral in black here, then it starts to feel more like something that you have a hope of solving by sort of standard methods. So that's sort of how I think about it now. Okay, so so we now know that this fact, right? That this is the expected total weight incident to the root in the component of the wired minimum spanning forest containing the root of the Poisson weighted infinite tree. Okay, and let's just let's use that together with this general convergence result of Wallace and Steele, which said that convergence, local weak convergence, also implies local convergence of the wired minimum spanning forest to deduce something about the total weight of the minimum spanning tree of a complete graph. Okay, so if you remember, we were writing Tn for the minimum spanning tree of Kn with these edge weights, which were uniform 0, 1s, right? Then the expected total weight of Tn converges to zeta 3 as n tends to infinity. So in fact, this fact can be strengthened to convergence in probability, but I won't do that in the lecture. Okay, so the proof isn't hard given what we now know. We just say, this expected weight, right, is the same as if we sum the weight over. So I want to relate this to the total weight of edges in the minimum spanning tree that are incident to a fixed vertex, say 1. Okay. So I need some prefactor here. Now by symmetry, right, each vertex has the same expected weight incident to it in the minimum spanning tree. Okay. So this quantity here doesn't depend on which vertex I choose to look at. Okay, but if I sum this over all the vertices, all n vertices, then I'm going to count each edge twice, once from each end. Okay, so if I sum this over all n vertices, I get twice the total weight of the minimum spanning tree, and that means that the weight, if I only sum over one vertex, I get 2 over n times the total weight of the minimum spanning tree. Right, so the factor n because I'm summing over one vertex instead of all n, and the factor 1/2 because if I did sum over all n, I would get twice the weight that I actually want. Okay, so that tells me now that if I write that as n over 2 times, and now I'm going to multiply and divide by n because the thing that we had convergence to the minimum spanning tree of the PWIT for was with weights n times these uniforms, right? So n times UE. And I really meant to do that. Okay, so once we multiply here, then now the fact that the complete graph with these weights converges to the Poisson-weighted infinite tree tells me that this expectation converges to the total weight incident to the root in M. Okay, so this is converging to 2 zeta 3. Okay, and so this whole quantity here converges to n over 2, 1 over n times 2 zeta 3, which is just zeta 3. Okay, so that is just a very soft argument, just double counting together with this general convergence result tells me about the expected total weight in the minimum spanning tree. Okay, so one other way to think about this. Well, okay, so let me finish there and just say, another way to think about this factor zeta 3 emerging, or really about this integral here emerging, is if you think about the coupling between the random graph process and Kruskal's algorithm. So when you're looking at the graph Gn lambda over n, you know that you have some component that size is about n theta lambda, okay, and then a bunch of sort of tiny components out here. And when a new edge comes along in the graph process, it'll get added to an edge that comes along at this time will have weight about lambda over n, and it'll get added to the minimum spanning forest if and only if its endpoints are in distinct connected components of this picture. Okay, but the odds, effectively, because everything aside from the big component is really small, effectively the only way for both endpoints to land in the same component is for them both to land in the big component, or at least that's the overwhelmingly most likely way for a random edge to have both endpoints in the same component. So the probability that an edge that comes along around this time doesn't contribute to the minimum spanning tree is roughly just 1 minus the probability both of its endpoints fall in the giant component, which is 1 minus theta lambda squared. Okay, and then if it does contribute, it contributes weight about lambda over n, because that's the weight of the edges that come along around here. Okay, so that's another way to see where this integrand comes from, and that's one route you can use to strengthen the convergence of the expectation to a convergence in probability. Okay, so what I want to do with the rest of the course, the rest of the lecture, is to talk to you about a little bit more about the structure of this wired minimum spanning forest M, and in particular to explain to you that it's a one-ended tree. Okay, so that'll take a little bit of thought. But before I get to that, I just want to make a couple of brief, as I said, administrative remarks. So I guess administrative and social. So first, the admin. So I'm putting a link in the chat, which I'm hoping that you can all and requesting that you can all fill out. So it's just a brief demographic survey. We're hoping to find out, who's been attending. It's anonymous, and the information will be given in aggregate to the various research institutes that sponsored the school, CRM-PIMS, MSRI. I emailed about that as well, but I know there's some subset of you that don't always get the emails I send. So grab the link now if you don't have it in email, and please do make time to fill it out. It only has 7 sort of multiple choice questions. It's very short. And the second thing is that at the end of this lecture, we'll have a sort of end of school social gathering on GatherTown at the regular link. Thomas, maybe you can pop that into the chat when you have a sec, or someone else who has it handy can do that. So, I'll probably take 5 minutes at the end of the lecture, and then I'll pop over there. JC is going to come back as well to say hello. I hope some of you will stick around to, raise a glass together to a good school. Great. So then going back to the lecture, there's a question in the chat, why is there a square on theta here? So I was saying in order for an edge not to be counted, both of its endpoints have to fall in the same connected component when an edge comes along. So the probability that they both fall in this component, the two endpoints, is, well, the probability for each one is theta lambda. So the probability they both fall in is theta lambda squared. And the probability that they both fall in one of these tiny components is sort of an order 1 over n correction. Good. So now we're going to turn to the structure of M. Okay, and so to get at this will take a couple of steps. So there are a few different objects that are going to play, and but when there's a variety of different trees around, it can be easy to get confused. So let me remind you of what we have. So there's the wired minimum spanning forest itself, okay, which we had two ways to think about. One is in terms of saying an edge is in the wired minimum spanning forest if and only if both of the components of the percolated graph are finite. So when you look at the weight of the edge, you remove all the edges of that weight or bigger, and you see whether the two endpoints are already both in infinite components. If they are, you leave the edge out. If they're not, then you put the edge in. Okay. Sorry, that's a F. That's one way to think about it. Another way to think about it, about the wired minimum spanning forest, is just as the union of all of the trees that Prim's algorithm builds. So you run Prim's algorithm once from every vertex of the PWIT, and you keep all the edges that any of them join. Okay, so those are those give you the same picture, and both of those are are spanning forests, if you like, and so M is one of the components of the spanning forest. It's the one that touches the root, but there can be other there are other components hanging around here and there as well. Okay, so that's one of the trees that factors in, or one of the things that factors in the whole wired minimum spanning forest. Another one is what I'll call T infinity. So T infinity will actually be sort of the crux of the analysis. So this will be the tree built by Prim's algorithm. On the PWIT, starting from the root. Okay, so this is a subtree of the minimum spanning forest, because, I mean, it's a subtree of M, because, right? The whole wired minimum spanning forest takes all of the trees built by Prim's algorithm from everywhere and takes their union. And so that when you take the union of all of those, it can add in some other components to this tree T infinity. Okay, but we'll start by studying T infinity and then move from T infinity to studying M. Okay, so we're going to prove that so M is one-ended. Okay, so that means that if gamma and gamma prime are two paths in M, simple paths, then the symmetric difference of the two paths is finite. Okay, and we called this T empty set before. I can't swear to that. I am going to use the notation. So there's one other sort of tree that's going to come up today, which I'll write like TUX. Okay, so this is like the subtree rooted at X, rooted at U, with only edges of weight at most x. Okay, so I'm pretty sure I used this notation in last lecture. And remember that, so this, right? So this just says every node, you look downwards, and when my drawings now, it's downwards. So you look downwards from you, take all the edges of weight at most x. Then from whoever you chose, they look downwards, take all edges of weight at most x. And this is distributed as a bien-aimé, Poisson X bien-aimé. Okay, not independent for different nodes, but from any fixed node, it's Poisson X bien-aimé. Okay, so the first step in proving this proposition is proving this theorem is going to be to prove that T infinity is one-ended. Okay, and once we know that T infinity is one-ended, then we'll need to show that that all of these additional gluings that come from taking the union of all of the trees, all of the Prim trees, doesn't create additional ends on that get attached to T infinity. Okay, so that's our strategy, and the picture that we're going to develop for T infinity in order to prove this is quite a lovely description. It was sort of first derived in the setting of invasion percolation on regular trees by Omer and three co-authors, Jesse Goodman, Frank Den Hollander, and Gordon Slade. And then with a couple of co-authors, I sort of revisited that picture that I'm about to tell you about in the setting of the Poisson-weighted infinite tree. So we're going to end up with a picture that's sort of like what we drew in the Euclidean setting, where we have some sort of sequence of finite trees that are joined by some critical edges, which kind of hook you into, if you like, subtrees where percolation occurs. Okay, so if you remember that picture I drew sort of over on the right-hand side of the page when we were studying Euclidean percolation, where you hook into an infinite component and then continue exploring within the infinite component, and so on. We're going to draw a version of that same picture, those sorts of ponds in the Poisson-weighted infinite tree. Okay, so to develop that picture, I need a lemma. So if I write lambda naught for the largest edge weight ever added by Prim's algorithm, starting from the root, empty set. So that's the largest edge weight of T infinity. Okay. Then, so this lambda has density theta prime of x, where theta is, as before, the Poisson survival probability. Okay. And there's a unique edge of T infinity with weight lambda almost surely. Okay, so that says that when Prim's algorithm starts exploring from the root, it adds some edges here and there. Eventually, it adds an edge of weight exactly this weight lambda naught, and then after that, all the edges that it ever adds have weight smaller than lambda naught. Okay, so let me prove the lemma to you. So the fact that that this supremum has this density is not hard, because we always add the smallest edge available to us, right? So saying that the largest edge weight we ever add is at most x is equivalent to saying that starting from the root, we have infinitely many edges available to us of weight at most x. But that's just saying that the tree, when we do when we do the x percolated tree, we look at what's available to us with weight at most x, that has infinite size, right? But we just said that this is a Poisson X bien-aimé tree, right? So the probability that it's infinite is just theta x. So that says that the probability lambda naught is at most x is theta of x. Okay, so that indeed shows that lambda naught has density theta prime. Okay, so that's easy. And now, is that density with respect to Lebesgue measure? That's correct. That was a question in the chat. Okay, so is the logic behind this identity clear? Anyone have any questions? Okay, so now I'd like to argue that there really is an edge of exactly this weight. So let's do that in steps. So let me write F1 I want to start by thinking about what happens if we only do critical percolation on starting from the root. Okay, so if I look at the tree, you know, T theta 1. So I only have edges of weight at most 1. So that's a critical Poisson bien-aimé tree. So it's almost surely finite. Okay, and so I can look at the smallest weight edge leaving this finite tree. Okay, so I'll let F1 be that edge. So this is the smallest weight edge leaving T1 at the root. Okay, and then I'll write, so let's say that the weight of that edge is X1. Okay, so here, let me draw that a little bit more schematically. We have, you know, this blob, which is the first, this critical tree, and then somewhere leaving the blob, we have an edge F1. Okay, so, sorry, an edge X, F1, whose weight is X1. Okay, and now I want to inductively, you know, my first threshold was 1, but now I'm going to increase my threshold for exploration and explore everything connected to here whose weight is at most X1. Okay, so I'll that'll get me some more tree. So inductively, you know, for k at least 1, if when we do the sort of percolation at threshold xk, if what we see is still a finite tree, then we'll explore some more. So we'll let fk plus 1 be the smallest weight edge leaving this tree. Okay, and we'll again write, you know, xk plus 1 for its weight. Okay, so the picture then is we explore this first tree, we add some edge that increases our weight threshold. This was the smallest weight edge that left the first tree, right? X1. So whatever we explore at the next step, you know, will only be down here. This is the new part that we get that gets added in order to build the tree. You know, this bigger tree is T theta X1. Okay, but if this is a finite tree, then now we add the smallest weight edge attached to this tree. That could be anywhere sitting on the tree. Maybe it's over here, right? So here's the edge F2, and then that gives us a bigger threshold value X2, which will, you know, increase the subtree we explore by adding a new pendant piece. Okay, and now the idea is that so the first step is guaranteed to be finite, but each of the subsequent steps has a probability bounded away from 0 of attaching an infinite tree, because this, you know, this value X1 is greater than 1. So when we start at this, at the far end point of this edge and explore all of the descendants that you can get to by only looking at edges of weight less than X1, that's a supercritical Poisson bien-aimé tree. So you might add an infinite tree, okay? And the next tree, this edge has an even higher weight, so the next tree you explore is even more supercritical, so you have an even better chance of adding an infinite tree. So this process can't go on for unboundedly many steps, adding bigger and bigger trees and getting gradually higher and higher values. It only goes on for a bounded number of steps and then adds an infinite tree. Okay, so that's why we end up adding, there's a unique edge of this weight, lambda naught. But let me just write that down a little bit more carefully. Hi, David. Conditionally, given the tree, the sort of kth step of this process, the next edge weight, what's it distributed as? Well, it's the smallest. What we know after k steps is that all of the edges leaving this bubble are bigger than xk. Okay, and so each node here has a Poisson process of edges attached to it, and we're taking the next weight, which is the first weight bigger than xk. So for a given node, the first weight bigger than xk will just be xk plus an exponential, but we get to take the minimum of all those exponentials over all the nodes in the tree. Okay, so the minimum of a bunch of exponentials is another exponential with a higher rate, and so xk plus 1 is distributed as xk plus an exponential with rate, the size of the tree we've grown so far. Okay, and then the size of the next tree that we expand to, the xk plus 1 percolated tree, will then be distributed as, so whatever we already had, plus then the thing that we attach on is like a Poisson bien-aimé tree with this new parameter xk plus 1. And the point is that parameter is always bigger than at the first step x naught. We can say that this new size is stochastically bigger than, so t naught xk plus the size of an independent Poisson bien-aimé tree with parameter x naught. Okay, and so since x naught is almost surely bigger than 1, this implies that the number of steps, the number of times we have to do such an exploration before we finally hit upon an infinite tree is stochastically bounded from above by a geometric whose parameter is, well, the probability that we get an infinite tree at the very first step is just the survival probability of Poisson x naught bien-aimé, which is theta of x naught, and that probability only goes up as the steps go on. Okay, so this is finite almost surely. Okay, so why does knowing that this process is finite almost surely tell us that lambda, that there will be an edge of the tree T infinity, the Prim's tree from the root that has weight lambda naught? Well, what does Prim's algorithm do? It always goes for the smallest weight edge, right? So it will first explore all of these edges because they all have weight less than then I guess that should have been x. Maybe that was x. Sorry, there was these knots. I started at 1, not at 0. So these should have been 1s and not 0s. Right. So Prim's algorithm. Sorry for the confusion. So Prim's algorithm is going to, starting from the root, we'll first explore all of these edges because they all have weight less than x1, then all of these edges because they have weight less than x2, then all of these edges. Okay, and the first time it finds itself in this process at the root of an infinite tree, if this green tree here is infinite, then Prim's algorithm will add this edge of weight x2, and after that, all the other edges will have weight strictly less than x2. Okay, so in other words, you know, the value lambda naught will just be the value xk, the first value xk for which the next tree added is infinite. That will be the largest weight edge Prim's algorithm will ever explore, and then it'll have an infinite route to explore of strictly lower weight edges. Okay, just looking at the chat, no edge heading out has weight less than fk plus 1. That's correct, yes. Yeah. So because we were always choosing the smallest weight edge, leaving anywhere in what we'd grown so far, that guarantees that Prim's algorithm will be forced to take all of these edges xi until it hits upon an infinite tree. Okay, so that that shows, you know, that was the sort of, what that really was a sort of multi-step analysis, and all it built for us was what Prim's algorithm explores until it gets to the highest weight edge that it ever adds. Okay, so all of this, if you like, you know, this picture of, you know, of trees that we, you know, we're growing here, that's kind of just one step in a process that now found us this edge lambda naught. Okay, so Prim's algorithm will explore all of this, then it'll explore lambda naught, the edge of weight lambda naught. And now, right, because this is the largest weight edge that Prim's algorithm ever explores, that means all of the other edges leaving what came before have weight bigger than lambda naught. And on the other hand, in exploring this edge, we must have reached the root of a tree that has infinitely many values of weight less than lambda naught. Okay, so after we explore this edge, Prim's algorithm will only explore in that subtree. Okay, now, and so that's the sort of, you know, this multi-step process really gave us a first step to get us going on defining the structure of the tree T infinity. Okay, so now I want to, with that lemma proved, we're now going to prove this proposition which says that T infinity is one-ended. Okay, so let's let me write so E naught for the edge from the edge of weight lambda naught. So this is the edge U naught V1. Okay, so this is for the unique weight lambda naught edge of T infinity. Okay, and then so I'll call this this first bubble over here, which now I want to ignore its internal structure. That was just really for the sake of proving that that bubble existed. So I'll call this bubble T0, okay? And I'll call everything to the right temporarily, so T infinity 1. Okay, so that is, I'm letting, so T naught be the component of T infinity minus this edge E naught containing U naught, and T infinity 1 be the component of, after removing this edge, which contains V1. Okay, and now I want to look at the largest weight edge that's ever added in T infinity 1 by Prim's algorithm. Okay, so I'll let lambda 1 be the largest weight PE, where E is an edge of T infinity 1. Okay, and now we can likewise derive the distribution of lambda 1. Okay, well, really, it's easier to write down the conditional distribution of lambda 1 given lambda naught, right? So what's the probability, you know, over here we know that you can explore infinitely far with edges of weight less than lambda naught. So that's just saying that the sort of, when you do percolation with parameter lambda naught on this tree, you see an infinite tree. And now we want to know how much you can lower the parameter and still get an infinite tree. right? So this is the same as the probability that, so the tree rooted at V1 percolates at parameter X, given that it percolates at parameter lambda naught. Okay, well, that's just the, I mean, because these events are nested, if it percolates at the smaller value, it also percolates at the bigger value. That is just the ratio of the two probabilities. It's the probability that it percolates at parameter X divided by the probability that it percolates at parameter lambda naught. And that's theta X divided by theta lambda naught. Okay, so that means that conditionally given lambda naught, lambda 1 has density theta prime over theta lambda naught, if you like, on the interval from 0 to lambda naught. Okay, and so we can tell sort of we now can describe the distribution of the largest weight edge we'll ever add after adding lambda naught, and we can likewise show that there's going to be a unique edge of weight lambda 1. So E1, which I'll write U1 V2 of weight lambda 1. And now you can see I'm just going to continue in this matter. So inductively, I'll define a sequence of edges, EK, right, where each time EK is just the largest weight edge that Prim's algorithm ever adds after having added edge EK minus 1. Okay, so EK is UK VK plus 1, and so TK will be the component. So the first, let me draw refine this picture now. We're going to have another blob, which is T1, and then the largest weight edge ever added after this first edge E0, which will be the edge E1 of weight lambda 1, connecting U1 and V2, and then that will connect us to T infinity 2, and we can further refine that picture, right? So by looking at the next largest weight edge we ever add, which will be, connecting U2 with some vertex V3, and then so this is T2, and this will be T infinity 3, which we can further sort of collapse into blobs in the same way. So TK is the component of T infinity when you remove the edges E0 up to EK, which contains UK, and then T infinity K plus 1 is the component when you remove these edges that contains the far endpoint VK plus 1. And then lambda K is the weight of EK, which is also the largest edge weight that's ever added within the tree T infinity K. Okay, and now I'm writing it as a max and not as a premium because I justified the first step, but the same sort of argument shows that at every step there is a unique edge of this weight. Okay, so you really have this sort of picture. Okay, and now, after, the key point is that, after exploring this edge, because we have infinitely many edges of weight less than lambda 2 to explore within the subtree rooted at the far endpoint, that means all subsequent exploration will be exploration of descendants of this vertex V3. In particular, lambda 3 will be a descendant edge, will be sitting on a descendant edge of V3. Okay, so what structure does this give us? It gives us the structure of a bunch of finite graphs attached in a line by a sequence of edges, right? But that immediately implies one-endedness, right? That any infinite path has to just follow through these graphs. And there's really only one way to follow through the graphs because they're trees, right? I mean, if you want to have an infinite path, maybe you can start off by, because you were at some leaf which wasn't on the path between V1 and U1 here, you have to hook into that path. But if you want to be an infinite path, you're going to have to then just follow on your way out here. Okay, so this construction itself, the description of T infinity that we've given here tells us that, so UK plus 1 is a descendant of VK plus 1 for all K. And then after adding EK, so all the edges added by Prim are descendants of VK plus 1. And so this implies one-endedness. Okay. I think I gave a definition of one-endedness which is slightly stronger than the standard definition. I think the standard definition is just that if you remove any finite subset of the graph, then what's left is a unique infinite. There's only one infinite connected component in what remains. Okay, whereas I was actually insisting that the paths coincide. In this particular situation, the paths do coincide, but I should say that that's a stronger notion than the term one-endedness is usually used for. Okay, but it's also clear that from this picture that if you remove any finite subset of the graph, then there's only one infinite component. It's sort of the thing going off the page to the right here. Okay, so I think that should convince you that that the tree T infinity is one-ended. Now I'd like to extend from this tree T infinity to understand M, right? That we've proved the proposition, and now we want to prove the theorem. Okay, but before I do that, I want to just collect a little bit of information about T infinity, just because this is already a pretty picture, and we can say a bit more about it. It's worth recording. It'll be the last exercises I leave for you, but I don't expect there to be much of an exercise session today. But these are sort of things that are worth thinking about if you like the topic, because you get some pretty sort of explicit formulas for various quantities in this picture. Okay, so I'll start with just recording a corollary, and then I'll state an exercise. So the corollary is just that for any positive, for any x greater than 1, almost surely, so T infinity only has finitely many edges of weight greater than x. Okay, and that just follows from the description of the sequence lambda I, right? So if we just look at these edge weights lambda I, we get a Markov. I mean, we describe the transition probabilities. The conditional distribution of lambda I plus 1 given lambda I, and that gives us a Markov structure. So this is a Markov process on one infinity with transition density. So PLX is theta prime of x over theta L. For x in 1L. Okay, and so, I mean, in particular, lambda I converges to 1 almost surely, right? So at each step, this is just saying we've conditioned on this tree being infinite. How much can we lower the parameter and stay infinite? Okay, well, if you think about what's the picture of theta, right? It just has slope 2 near the critical value 1. So once you get close to 1, really you're just the amount you can lower the parameter and stay infinite is just going to be a uniform fraction of the remaining gap between x and 1. Okay, so you're basically cutting the distance to 1 by a uniform distance at every step. So this sequence tends down to 1, right? And if lambda I is less than x, then that means that after we add this edge lambda I, all the edges have weight less than x. Okay, and which means that all edges of weight greater than I have to be in the first of weight greater than x have to be in the first I trees. So all edges of weight greater than x belong to one of T naught up to Ti. Okay, and these trees are all finite. They're those initial ponds, and so that tells me that I'll only have finitely many edges of weight greater than x. Okay, so the exercises I'd like to leave you with now. So you can actually describe not only the sequence of edge weights, but you can also describe the sizes of the trees quite explicitly. So the probability that one of these ponds, these trees TK, has size m, given that, so the only information you need for this turns out to be the next sort of outlet threshold, lambda k plus 1. This is theta y over theta prime y times e to the minus my to the m minus 1 over m minus 1 factorial. Okay, which can be rewritten as theta y over theta prime y times m times the probability that a Poisson bien-aimé with parameter lambda has size exactly m. Lambda hat, sorry, the dual parameter. Okay, so what's this saying effectively is that if I tell you the largest weight that you'll ever see, the pond that this tree Tm that you build, or Tk plus 1 that you build, looks like now a subcritical Poisson bien-aimé tree, okay? Except its distribution is biased by its size. So it prefers, this prefactor m out front means you have a size biasing of the size of the tree. Okay, so this is, I'm not claiming that this formula is obvious, but it's also like everything is explicit enough that it's not too hard to find it, and it's really a nice explicit formula. It allows you to, well, now we have a very explicit Markov process for the lambdas and a very explicit conditional description of the sizes of the ponds given the lambdas. Okay, and using that, so that's part A of the exercise. Part B of the exercise is to find the asymptotic distribution of pond size as you go, once you go for a long time, so once k is large. So if I write fyx for the probability that this pond, I'm calling these finite trees between the maximum edges ponds, obviously. If I write, so fyx for the probability that this tree has size at most x over y minus 1 squared, given that lambda k plus 1 is y. Okay, so that's, if I define fy in that way, then fy converges to a cumulative distribution function as y tends to 1. Okay, so what this is saying is that, well, in particular, what it's saying is that when y is very close to 1, the size of a pond when lambda has that value is of order 1 on y minus 1 squared, right? So if we think of y as 1 plus epsilon, then we're saying the pond size is 1 on epsilon squared. And now these values, remember, are getting geometrically close to 1. Each one, once they're close to 1, we said each one is getting a constant factor closer to 1. Okay, so that means these trees are quadratically big in that error, that distance to 1. So the ponds are actually growing geometrically in size. Okay, and quadratically relative to those edge weights. Okay, and it turns out, so there's even more sort of magical distributional properties in this picture. It turns out that if you look at the number of edges along this path in the pond, that it's conditional on the next maximal weight. It's exactly geometrically distributed. So in some sense, you have to just sort of wait there's some holding time along the unique infinite path until the next maximal edge comes along. And then you drop and the next holding time is longer because you are waiting for a sort of more critical edge. Okay, so, but I won't get into all of that. This is just to say, to describe the pond sizes as a function of those maximal edge weights. Okay, so from this, I won't do the details. I don't have time, but you can prove using just this exercise that that T infinity has quadratic volume growth. Which is to say that if I look at the number of vertices in T infinity whose distance from the root is at most n, that this grows like n squared in probability. Okay. There's a question in the chat. Is this also true conditionally on everything before up to step k? I'm not sure exactly what that is in reference to, but maybe I can answer that at the end of the. We can return to that at the end of the lecture, because I'd like to get through the explanation of how to build M from T and see that it's one-ended, and that's still a little bit to do in the next half an hour or so. Right. So we have this, let me draw it vertically now. We have this tree, so T infinity. And we'd like to understand how M, how this tree sits within M. And, the goal is, again, M is also one-ended. Okay, so let me do the following. So remember that for an arbitrary vertex U sitting inside the tree, the Poisson-weighted infinite tree U, then we defined TU lambda to be the subtree containing edges of weight at most lambda. And let me define, let me write, so tau of U for the largest value lambda for which this tree is finite. Okay. And now I want to think about, so this is an important parameter for me for understanding how M lies within T, how T infinity lies within M. Okay, because if I look at an edge here, which goes from T infinity to the rest of the graph, okay, T infinity is itself here sitting within the Poisson-weighted infinite tree, right? This is U. Okay, and if I want to understand whether or not this edge is going to get added when we go from t infinity to m, I need to know about whether the component sitting at v, the subtree rooted at v, is infinite when the parameter is this value here, right? So that is to say, right, if I look at an edge uv, so this is an edge of u, with whose near endpoint is in t infinity and whose far endpoint is not in t infinity, right? Then we know that the weight of this edge, so PUV, is bigger than it's bigger than this value here, right? Because when Prim's algorithm explored, it chose to add this edge instead of this edge at some point, right? It had both edges available. It chose the smallest weight edge, and that edge was lambda 2. Okay. So let me actually label all the vertices in this. Let me assign a sort of value lambda to all of these vertices. So lambda, I'll say that lambda u is defined to be lambda I if u is in Ti. Okay, so this vertex has lambda of u is equal to lambda 2. Does that make sense? Okay, so that means that if I look at the subgraph connected to u, containing only edges of weight lambda u, right? That's an infinite subgraph. It contains everything in here. It might not contain what's up here because lambda 1 it doesn't contain what's up here because lambda 1 has weight bigger than lambda 2. But if I only look at edges of weight at most less than PUV, I will contain the edge lambda 2, and then I'll contain a path down to infinity here, right? So that there's, I mean the green graph. So there's a question I missed in the chat. What is the large U? So this is the Poisson-weighted infinite tree. It's the whole tree that everything is happening within. Okay, so U stood for Ulam-Harris. It was our sort of set of vertex labels for the vertex set of that tree. Okay, right. So the only subtle point in what I'm saying right now is that we're interested in the component. So we remove all edges. We're interested in understanding whether when we remove all edges of weight PUV or more, whether both endpoints are in infinite components. Okay. But this is not the same as looking down in the tree anymore. The path from U can go up in the tree and then back down to get out to infinity here, as long as it only uses edges of weight less than PUV. Because of that, we know that U does have an infinite path of weight less than PUV because this edge lambda 2 has weight less than PUV because it was added and UV wasn't. Okay, so there's a path from here that somehow gets out this edge and then continues on forever. Okay, so that means that so one of the components, when we remove edges of weight PUV or more, one of the components is infinite. And we only add this edge if it's not the case that both of them are infinite, right? In order to add the edge in the wide minimum spanning forest, we need both of those components to be finite. And we just failed with one of them. One of them is infinite. So that means that, if the other one is, infinite, if tau v, which is the threshold for this tree being infinite, if that's less than PUV, then that means that the subtree rooted at v at this value WUV, PUV is infinite, which implies that the edge UV is not an edge of M. Okay, and if TV is bigger than PUV, that means that the subtree rooted here at this value is still finite, which means that UV is an edge of M. Okay, so that's our criterion for whether or not a boundary, a boundary vertex attached to here will have its will be added to the to M. Okay, it's just whether or not at that value its subtree percolates. Okay, it's a long-winded way of saying just because we do percolate inside of T, in order to get added, we can't percolate outside of T. Okay, so what we're going to do now to grow M is start from T infinity and add in all of the components, all of these trees which get added according to this rule. So if this edge gets added, then its whole subtree will also get added because that's some finite subtree, which then we've just learned this is the cheapest way for it to get to infinity. Okay, so we'll add all of those. And then once we add all of those, then we'll repeat. We'll look at the boundary of what we get and we'll see what else gets added in the same way. Okay, so let me set that up. So this is the last, okay, I know there's a lot of iterative constructions in this proof. First, we did an iterative construction to figure out that these forward maximum weights were unique. Then we did an iterative construction to build the tree T infinity. And now we're doing one last iterative construction to build M from T infinity. Okay, so we'll do that and then we'll basically be done the course. So the first one, the first step, we start from T infinity. We'll write, so partial M naught for this edge boundary. So these are the edges UV, where U is in M naught and V is not in M naught. Okay, and then we'll let, so M1 be everything that gets added on when we sort of according to this rule for whether or not these neighbors get added to the tree. So which trees do we add on? We add on the trees TV, PUV, whenever this thing is finite. So for UV in the boundary, so these are boundary edges where tau V is bigger than PUV. Okay, so we checked whether this edge gets added, but now when we add that edge, we also know that we'll add the whole subtree, so we're just gluing that whole subtree in TV, PUV. Okay, so that's one step. And then inductively, so if we've already sort of we glued K layers, then we'll let the K plus first layer, or the K plus first graph, be the kth graph plus everything that gets added on in the K plus first layer. So that's, again, trees of the form TV, PUV. But now UV should be in the boundary of the kth tree, and we still want that TV is bigger than PUV. Okay, so for exactly the same reason now, if we look at an edge that attaches to this tree, right, what matters is whether this edge has, so this edge will have weight bigger than this first PUV, right, because it wasn't part of this tree. And now, so anything in here has a path to infinity where the largest edge weight is this edge weight here. Okay, and so the question for the tree down here is, does it percolate at this threshold value PUV? Okay, so that's our notion of boundary, and so we'll some vertices won't get glued on, some will, but if we glue on another subtree, then now we have a subtree, right, where for everything in this subtree, the largest weight edge on the cheapest path to infinity is this second boundary edge here. So this is the new threshold. And when we do the third layer of gluing, we need to see whether the subtree is infinite at that threshold, and so on and so forth. Okay, so that's just a way of constructing the wired minimum spanning forest in layers, right? Anything that joins on has to join on in a finite number of steps, which means it has to join on in a finite number of these layers. Everything is at a bounded distance. It has to be in one of these trees. So then that means that the final tree M is just the union of all these layers, or in other words, it's the limit of mk as k tends to infinity. Okay, and so now the key to proving that this tree is one-ended is just to say that this sequence of layers can't create infinite paths. Okay, so we don't want these. There's a question. Sorry, I just got distracted by a question in the chat. We don't add UV here. So I'm focusing here on the vertex sets of the trees. So telling you, if I tell you the vertex set of the tree, you can tell the whole tree, right? And so in the vertex set of T naught, of T infinity, of M naught, U is already there. And then I add V, the far end point, if I add this tree. So I didn't explicitly say that the edge was there, but that's just because I'm only focused on the vertices. Yeah. Okay, so what we don't want to happen if we want M to be one-ended is for these layers to build up and create infinite paths. Okay, so to check that that doesn't happen, we'll just check that actually the expected size of the whole subtree rooted at one of these nodes of all the layers altogether is finite. Okay, and so there's one calculation I don't, the sort of formula that gives that to me. I don't quite have time to prove in full detail, but I'll sort of tell you where the parts come from. So if I look at one of these boundary edges, UV, okay, and some value lambda greater than 1, if I look at the expected size of the subtree of M rooted at V, given that the weight of that boundary edge was lambda. Okay, so I'm saying, I tell you this value is lambda, and I ask for the expected size of all of the layers that get added after that, that are, all of the descendants of V in the whole tree M. Okay, then that's the sum k at least 1 integral over lambda 1 less than lambda 2 less than lambda k, and then the product for I from 1 to k, e to the minus lambda I minus lambda I hat. So that's the Poisson dual parameter over 1 minus lambda I hat d lambda 1 d lambda k. Okay, so I'm not going to prove this to you in detail, but I'll explain the formula to you. Okay. So basically, the sum is telling you about how many layers you go out. So you're interested in computing the expected size of this subtree. So you can think of splitting that into layers and asking for the contribution from each layer. So the k term in the sum is the kth layer, and then you need to ask how far up the parameter has gotten. So these values are getting larger and larger along here, lambda 1, lambda 2, and so on. So the integral is tracking how high the values get. Okay, and then the expectations in the numerator are basically what's enforcing. There's a little bit of, to get this version of the formula, you use the defining identity for Poisson, for the Poisson survival probability, to simplify things a little bit. But basically what the numerator is doing is enforcing that you've only seen finite trees along the way. Okay, and then the denominator is telling you about the size of those trees. Because remember that for a subcritical, if I look at the size of a subcritical Poisson, well, or actually any branching process, right? The size of a subcritical branching process is just 1 over 1 minus lambda. So that's when lambda is less than 1. Okay, so this is really telling you about the sizes that you get along the way. Okay, and the product structure, the reason you have a product of the sizes is because, if the first tree has size 15, that gives you 15 spots to grow second trees from. Okay, so you really do have a kind of multiplicative form for that. Okay, and so, you know, I haven't given you a full proof for this formula, but I think I've at least told you kind of where the parts come from. And so now, you know, using that formula, we can prove that that M is almost surely one-ended. Okay, and so, you know, we only have to check that this integral is finite once, because, you know, this boundary has only countably many edges. It's you know, the boundary of a, well, I mean, the whole Ulam-Harris tree only has countably many edges. So this subtree also, you know, this is a subset of that. So this has only countably many edges. So it suffices to show that almost surely for any single edge of the boundary, almost surely its subtree is finite. So the subtree reared at V is finite, right? And so that means, you know, it suffices to show that this integral, right? We know we know that this integral is telling us about the expected size of the subtree given that edge weight, right? So as long as this expectation is finite for any fixed value of lambda, then the tree is almost surely finite, because lambda just takes some value. Okay, so it suffices to show that this thing is finite for any lambda greater than 1. Okay, and so let's just bound this. Okay, so right, so I think I'll start by you know, writing this as an integral, so symmetrizing, so that the lambdas don't have to be ordered, and that gains me a factor of 1 over k factorial. Okay, so I can write this as 1 over k factorial, and then the integral of over lambda 1 up to lambda k greater than or equal to lambda of as, well, no, I'm going to write it product from 1 to k e to the minus lambda I minus lambda I hat over 1 minus lambda I hat. Okay, and now as lambda gets bigger, lambda hat gets smaller, right? The supercritical tree conditioned, the more supercritical it is, then when you condition it to be finite, the more subcritical it is, right? So lambda decreases as lambda hat increases. Okay, so that means that these denominators, right, the 1 over lambda hat factors give you the biggest contribution at lambda. So this is at most the sum k at least 1 over k factorial, and then 1 over 1 minus lambda hat to the k, and then integral lambda 1 up to lambda k of e to the minus, still all at least lambda, and then e to the minus lambda I minus lambda I hat, d lambda 1 up to d lambda k. Okay, now again using that lambda hat decreases as lambda increases, right? I can bound this integral from above by pretending that the lambda I hats are always just lambda hats. Okay, and so if I do that, then this just turns into an exponential integral from lambda to infinity k times. Okay, so then that means that this whole thing is at most some k at least 1 over k factorial, 1 over 1 minus lambda hat to the k, and then so e to the minus lambda minus lambda hat, k times, so e to the minus k lambda minus lambda hat. Okay, so here I have something, some term which is exponentially either increasing or decreasing in k, but I don't care because it's beaten by a factorial term. So this whole thing is finite. Okay, so that integral actually isn't very hard to bound and show that it's finite. There's a question in the chat: isn't this the power series for the exponential? I don't think so because of this lambda hat. I mean, I don't know how that would play into. Yeah, this difference is changing in a nonlinear way as you vary the integrand. So I don't think it's just the power series for the exponential. Right. So what this shows is that this aggregate for any fixed vertex v here, the aggregate that gets glued on is a finite tree, and because that's true for every sort of boundary edge of t infinity, then all of t infinity only gets finite fuzz added to it, so the tree stays one-ended. Okay, and you can actually analyze, I mean, I just analyzed this process to prove one-endedness, but in fact, you can also use this aggregation process to get other information. So I'll just state without proof. So that you can use this to understand volume growth in M. So it turns out that almost surely, so M is like a three-dimensional object in the sense that the volume growth is roughly cubic. So if we look at the number of vertices of M, whose distance from the root is at most R, on the logarithmic scale, then that converges almost surely to 3. Okay, so this is, this is some indication that even though this integral, it was fairly easy to bound the, once you find this formula for the sort of size of the subtrees, that you could show fairly straightforwardly that the whole tree was one-ended. It's a little bit delicate because whereas the tree T only has quadratic volume growth, now this tree M that you build from T infinity has cubic volume growth. So really a lot of mass is being added. It just isn't being added in ways that create infinite paths. Okay, I wanted to. The timing worked out well to finish the lecture with a conjecture. It is possible to do a little bit better than this. You can get more quantitative information about this, how this volume growth behaves. I think that I have a preprint about this where I think I prove a sort of something like R cubed over polylog R as a lower bound, and then something like R cubed e to the something like root log R sort of upper bound. But my bounds are enough to get this sort of logarithmic asymptotics, but I think that it should actually be the case that the growth is really cubic in a stronger sense. So I would conjecture that if you look at this number of vertices at distance at most R from the root and divide by R cubed, that should converge in distribution to some non-degenerate random variable. And it would be very nice, finer information is known about T infinity. Like we sort of know how the random walk behaves on here, its typical distance from the origin, things like that. And not enough is known about M yet to say the same sorts of things about M. So there's actually it's probably a fairly fertile playground to study this tree in more detail. Okay, I think that wraps it up. I don't want to go over time because we have a social gathering to get to as well, but thank you all for listening. It's been a pleasure giving this course.
So I suggest we all unmute to thank Luigi for the lovely course.